Your phone is at 12%. You plug it in, and at first the number climbs with gratifying speed. Then, somewhere near the top of the charge, it slows down. The charger has not become tired, the electricity supply has not run out of enthusiasm. Inside the battery, lithium is arriving at a graphite surface faster than it can always move into the graphite beneath it. Under the wrong conditions, some of that lithium stops joining the graphite at all. It becomes lithium metal on the outside. That microscopic change is one reason a charging system may deliberately reduce the current. It is also the beginning of the honest answer to a very practical question. Does fast charging damage your battery? Sometimes it can. The useful question is when, where, and why. This film follows a graphite-based lithium-ion cell, the broad family used in many phones, laptops, and electric vehicles. Real cells differ in chemistry, design, cooling, age, and software. A number printed on a charger cannot tell you the whole result. To see what that number is asking the battery to do, we need to stop treating charge like a liquid poured into a bucket. When the battery powers your phone, lithium ions leave the graphite-rich negative electrode and travel through an electrolyte toward the positive electrode. Electrons cannot cross the separator with them, so they take the long route through the phone's circuit. That separated motion is the electric current doing useful work. Charging reverses the journey. An external power supply pushes electrons back toward the negative electrode. Lithium ions move through the electrolyte to keep charge balanced, cross a thin interfacial layer, and enter the graphite. Graphite looks simple because it is made from carbon. Microscopically, it is a stack of atom-thin sheets. Lithium can slip between those sheets and form ordered lithium-graphite compounds. This is called intercalation. It is closer to adding pages between pages of a book than filling an empty bottle. The host material has entrances, routes, preferred arrangements, and a finite rate at which its internal state can change. The lithium has booked accommodation. It has not been granted permission to enter through the ceiling. One ion arriving at the graphite has several pieces of work ahead of it. It must be carried through the liquid-filled pores of a thick electrode. Near the surface, it must shed part of the solvent structure traveling with it. It must cross the solid electrolyte interface, a protective film created by earlier reactions. Then it must transfer charge and diffuse through the graphite particle. Each step can be fast enough at a gentle charging current.
Raise the current, and the required flow rises everywhere at once.
This is where the traffic analogy helps, provided we do not mistake the ions for tiny cars. The electrolyte pores are routes through the electrode. The graphite surface is an interchange. Diffusion through graphite is the movement away from that interchange into the available storage material. High current sends more lithium through the system per second. But unlike cars, ions are driven by gradients in electrochemical potential. Their motion changes local concentration, voltage, reaction rate, and the phases inside the graphite. The traffic jam is not a row of impatient particles with headlights. It is a growing mismatch between the imposed current and the rates of transport and reaction. Near the separator, lithium can reach some graphite particles sooner than others. The surface region begins filling, while deeper regions lag behind. Lithium concentration in the electrolyte becomes uneven. Lithium concentration inside individual particles becomes uneven too. The system needs a stronger electrochemical push to maintain the same current. Engineers call the extra push polarization, or overpotential. At the negative electrode, that detail matters enormously. Graphite stores lithium at a potential already close to the potential of lithium metal. If transport is too slow and polarization becomes large enough, depositing lithium metal on the graphite surface can become competitive with inserting lithium into the graphite. An ion reaches the crowded entrance, gains an electron, and takes the wrong chemical exit. Instead of becoming part of an ordered lithium-graphite compound, it becomes an atom in a metallic deposit. Researchers have watched this competition happen. In operando microscopy experiments, different graphite particles lithiated at different rates. Metallic lithium appeared preferentially around regions that filled rapidly. During rest, some of the plated lithium moved back into the graphite. Some did not. That split decides whether the traffic jam clears or leaves wreckage behind. Freshly plated lithium is not automatically permanent damage. Some can be stripped away electrochemically or re-enter the graphite when the current stops and concentration gradients relax. But lithium metal is highly reactive in the battery's electrolyte. It can consume electrolyte and build more interfacial film. Parts of a deposit can lose electronic contact with the electrode and become electrochemically isolated. Researchers call that inactive material, dead lithium. It remains impressively lithium-shaped. It is simply retired from the battery business. Every atom trapped in inactive deposits or side reaction products is an atom no longer shuttling useful charge between the electrodes. The cell loses cyclable lithium. Resistance can rise. The remaining active regions are asked to work harder, which can make later charging still less uniform. In some conditions, plated lithium grows into porous, mossy, or filament-like structures. Filaments can increase safety risk and, in severe cases, contribute to an internal short circuit. But plating is not the same thing as an inevitable dendrite, and a dendrite is not the only way fast charging can age a cell. High current also generates heat. Electrode particles expand and contract as their lithium content changes. Interfaces continue to react. Cathode material can crack or degrade. Different cell designs distribute those stresses differently. So, the film's villain is not one silver spike waiting behind every fast charger. It is a control problem with several coupled failure routes. Now, return to the number on the screen. Why does charging often slow as the battery fills? Early in a charge, many systems can apply a high current, while the cell voltage remains below its upper limit. As the state of charge rises, the graphite contains more lithium, internal gradients become more consequential, and the terminal voltage approaches its allowed ceiling. A common charging method then holds voltage near that ceiling and lets current fall. More advanced systems may reduce current in steps or follow a model-based profile. Either way, the visible charging curve is being shaped around internal limits. 80% is not a universal chemical border. It is a useful public landmark that varies with the cell, pack, temperature, and software. One device may taper before it, another may hold high power beyond it. The percentage itself is also an estimate, not a microscope looking at every graphite particle. The general reason for slowing is real. Forcing the final portion at the same aggressive rate can demand more polarization, meet the voltage limit, produce more heat, and raise degradation risk. Temperature changes the whole contest. On a cold morning, electrolyte transport slows. Charge transfer across interfaces slows. Lithium diffusion within graphite slows. The battery can still show a perfectly ordinary percentage, while its safe charge acceptance has fallen sharply. Send the same current anyway, and the Q forms sooner. The electrochemical push grows larger. Lithium plating can begin at a lower charging rate than it would in a warm cell. This is why an electric vehicle may precondition its battery before a fast charging stop, and why charging software may restrict power when the cell is cold. Heating helps because transport and reaction kinetics usually become faster. That does not make hotter automatically better. Sustain a high temperature and other unwanted reactions accelerate. The interfacial layers can grow. Electrolyte and electrode materials age. Cooling too aggressively can preserve a cold bottleneck. Heating without restraint can trade plating risk for faster chemical degradation.
The battery would like to be warm enough to cooperate and cool enough not to acquire new hobbies.
A good thermal system therefore changes temperature with the task. It may warm the cell before high current, manage the heat released during charging, and remove heat afterward. The goal is a moving operating corridor, not the lowest temperature the cooling system can achieve. The charging controller has an awkward job. In a normal commercial cell, it does not have a tiny reference electrode reporting the exact potential at the graphite surface. It sees external voltage, current, temperatures, time, and a history of how the pack has behaved. From those measurements, calibration tests, and models, it estimates what may be happening inside. When should it reduce current? How much reserve does an aged cell need? Is one cold region in a large pack closer to plating than the average temperature suggests? Those are not merely software questions. They depend on particle size, electrode thickness, porosity, electrolyte composition, interfacial chemistry, cooling, pressure, and manufacturing uniformity. That is why two batteries connected to chargers with the same advertised power can experience different internal conditions. The charger supplies what the device requests. The battery management system decides what the pack is prepared to accept. The cells themselves impose the physical limit. Researchers are trying to move that limit, rather than merely approach it more cautiously. Thinner or more porous electrodes shorten transport routes, but can sacrifice energy density or increase cost. Smaller graphite particles shorten diffusion distances, but create more surface area for side reactions. New coatings and electrolytes can reduce interfacial resistance or make plated lithium more reversible, but each choice brings its own stability and manufacturing constraints. Charging protocols can also adapt. Instead of one fixed current, a controller can step the current down as risk rises, insert diagnostic pauses, use impedance signals, or combine electrochemical and thermal models. Laboratory methods can detect subtle signs associated with plating. Turning them into robust, inexpensive sensing inside millions of real packs remains active engineering. There is no single magic current that is fast for every cell and safe in every condition. There is a maximum useful rate for this cell, at this temperature, at this state of charge, at this age, under this cooling system. And that maximum moves while you charge. We can now answer the opening question without either comforting myth. Fast charging does not guarantee serious damage on every session. A well-designed cell and charging system can accept high power while managing temperature, voltage, and estimated plating risk. Nor is fast charging chemically free. High current narrows the margin when transport inside the cell cannot keep up, especially at low temperature and high state of charge. The wattage on the box describes the power available outside the battery. Battery health depends on the microscopic route taken inside it. The next time a charging curve races upward and then quietly bends, picture the graphite beneath the screen. Lithium crosses the electrolyte, reaches the surface, enters between carbon sheets, and spreads into the particle. The controller is trying to keep those steps in sequence. A battery is not a bucket accepting electricity. It is a crowded chemical transport system whose safest speed changes from moment to moment. The charger is not merely pouring more in. It is negotiating with traffic it cannot directly see. Stay silly.